Today we're going to start Chapter 5, Section 4. We're going to talk about something called the complex number system. But before we talk about complex numbers, first we're going to define what an imaginary number is. If you wanted to solve x squared minus 4 equals 0, there's a couple ways you can do it. You can either factor this into x plus 2, x minus 2, and solve it that way, or you can add 4 to both sides and get x squared equals 4. And then take the square root, the plus and minus square root, and x is equal to positive and negative. Square root of 4 is 2. So there's two answers, positive 2 and negative 2. You can do the same thing over here if you wanted to add 3 to both sides. You're going to get x squared is equal to 3. And then when you take the square root of both sides, you're going to get x is equal to positive and negative square root of 3. So there's two solutions here. But over in this third example, this one's just slightly different because you have to subtract 1 from each side, and you get x squared is equal to negative 1. And when you take the square root of both sides, you get x is equal to plus and minus the square root of negative 1. Well, if you pull out your calculator and you try to do the square root of negative 1, your calculator is going to give you an error that says it's non-real answer. It's not a real answer. And what that means is the square root of a negative number is not real. You can do the square root of any negative number and you're still going to get this error that it's a non-real answer. So instead of creating an error, what some mathematicians have done is they've defined a value for the square root of negative 1, and they said, well, this is not a real number, so if it's not real, then it must be imaginary. So they're going to call the square root of negative 1, they're going to use the symbol I, and I means it's an imaginary number. It's called the imaginary unit. So we use this I, this lowercase I letter, to represent the square root of negative 1. And that another name for that is the imaginary unit. I means imaginary. So here's a definition. A pure imaginary number is any number that can be expressed in the form of bi. Now this I is the same thing as the square root of negative 1, and b is any real number as long as it's not 0. I is the imaginary unit. So what you're going to do here is you're going to simplify these radicals and write them in terms of I. That means your answers are all going to have I's in them. And what I would suggest is as soon as you see a negative underneath a radical, you're going to circle it, you're going to pull it out and call it I. So this will be I times the square root of positive 4, because it's really the square root of negative 1 times the square root of 4. And the square root of negative 1 is I. So the next thing you can do is just simplify this radical. Well, the square root of 4 is 2, so this is just I times 2, but we usually write this as 2I. We just turn it around and write the coefficient first. The square root of negative 12, I take that negative out and I write it as I times the square root of 12. And the square root of 12 can be broken up into 4 times 3. So we're going to just call this I times the square root of 4 times 3. And when you take the square root of 4 out and call it a 2, you're going to get a 2 times an I on the outside and a square root of 3 on the inside. So that's simplified in terms of I. And here you have a negative underneath the radical, so you're going to pull it out and call it I. So it's negative 2I times the square root of positive 45. Remember that negative under the radical always becomes an I, if it's a square root, I should say. Now 45 can break down into 9 times 5. So it's negative 2I times the square root of 9 times 5. And the square root of 9 becomes a 3. Negative 2I times 3 is negative 6I times the square root of 5. Always remember that I is equal to the square root of -1. I've got a little star there because some people forget that along the line. Now, the most important power of I to remember is this, the I to the second power. If you square both sides on this one, you'll get I squared. And if you square the square root of anything, you're just going to be left with the radicand. So I squared is always equal to -1. That is the most important power of I to remember. So this should have a little star next to that. I squared is equal to -1 because you come up with I squared in a lot of different situations. Now what we're going to do is I've put a lot of different powers of I, starting with 0 and going up to 15. And you're going to start to recognize a pattern here, a pattern of answers that are going to come out. And I'll explain to you why this pattern is. So first of all, anything to the 0 power, like if you take 1 to the 0, 7 to the 0, you can grab your calculator, take anything to the 0 power, 100 to the 0 power, 77 to the 0 power. No matter what, anything to the 0 power is always equal to 1, and that includes variables. So I to the 0 is equal to 1. Anything to the first power is equal to itself. I squared is equal to, remember we said back here, I squared is equal to -1. And I cubed, well, that's the same thing as I squared times I to the first, right? I to the first times I to the second is I to the third, which means I times -1, which is -I. Okay, and those are 4 very important values that you need to remember. But hopefully you can just remember by anything to the 0, anything to the first, I squared is -1, and I cubed is I to the first times I to the second. Now we're going to go over to the second column. I to the fourth can be done a bunch of different ways, but I to the fourth is the same thing as I squared times I squared, right? I squared times I squared. Well, I squared is -1. -1 times -1 is 1. So I to the fourth is 1. I to the fifth is the same thing as I to the fourth times I. That's one way of saying it, one of many ways. Well, I to the fourth is 1, and 1 times I is I. I to the sixth. I to the sixth can be done a bunch of different ways. You can call it I to the fifth times I to the first. Well, I to the fifth is I times I is I squared. I squared is equal to -1. And I to the seventh is the same thing as I to the sixth times I to the first. Well, I to the sixth is -1, and -1 times I is -I. And look at this pattern of numbers, 1I, -1, -I. It's the same pattern as this column. And what you can do is you can continue in this same fashion. You can do I to the eighth is I to the seventh times I. I to the seventh is -I. -I times I is -I squared, and -I squared is -1, which is 1. I to the ninth is the same thing really as I to the eighth times I to the first. 1 times I is I. I to the 10th is I to the ninth times I. I times I is I squared, and I squared is -1. I to the 11th is I to the 10th times I to the first, which is -1 times I, which is -I. And you can go around again forever and ever and ever. You can get greater and greater and greater powers of I, 12, 13, 14, 15, but it's going to follow the same pattern. 1I, -1, -I. Now there's a shortcut, because sometimes we're going to be asked to find large powers of I, like I to the 101st power, for example, down here, or sometimes I to the 700th power. And we're not going to want to keep writing out all of these columns until we get out to the number that we need. There's a shortcut. This is the shortcut in finding a simpler power of I. To simplify a power of I, And I'm going to add to this little note, and I'd like you to add to the note that you never leave an exponent on I. Never, never, because it can always be simplified to one of these things. Never leave an exponent on the imaginary unit. Never. So if you ever end up with I to an exponent, what you're going to do is divide the power by 4, and you're going to use long division by doing that because you're going to get a remainder. I'm going to bring you back to 4th grade when you had to divide the long division way and note the remainder. And whatever the remainder is becomes the new exponent on I. And then the new exponent on I is going to be either a 0, 1, 2, or 3, and it's going to become one of these numbers in the end. So what this means is, well, this is really a 2-step process. What this means is you're going to take the power, which is 22, you're going to divide it by 4 with long division. Well, 4 goes into 22 5 times. 5 times 4 is 20, and when you subtract, you get a 2, and that is the remainder. I'll just put REM for remainder. So I to the 22nd is equal to I to the remainder. The remainder is 2, and I squared is equal to -1. So I to the 22nd is the same thing as I to the 2nd is equal to -1. If we wanted to continue this pattern like we did, we would eventually get up to I to the 22nd, and we would notice that it would be in this 3rd position down. I to the 101. Well, we take 101, the exponent, we're going to divide it by 4 through long division. 4 goes into 10 twice. Subtract and you get 21. 4 goes into 21 5 times, and you get a remainder of 1. So the remainder is equal to 1. So now what we have is I to the 101st power is equal to I to the 1st power, that remainder, and I to the 1st power is just equal to I, so that's our final answer here. So I'm going to go through these a little bit quicker now. Take 49, divide it by 4, and drop the 9 down, and 4 goes into 9 twice. So that's the remainder. So I to the 49 is equal to I to the 1st, which is equal to I. I to the 23rd. How many times does 4 go into 23? 4 times 5 is 20. You get a remainder of 3. So I to the 23rd is equal to I to the 3, and I to the 3 up here on this chart is equal to -I. I to the 32. How many times does 4 go into 32? Well, 4 times 8 is 32, and you get a remainder of 0. So I to the 32 is the same thing as I to the 0, and anything to the 0 is equal to +1. And the last example, how many times does 4 go into 17? 4 times. 4 times 4 is 16, subtract, and you get a remainder of 1. So I to the 17th is I to the 1, and I to the 1 is equal to I. So the answer to all of these questions are either going to be 1I, -1, or -I, depending on what the remainder is after you divide by 4. On the next page, what we're going to do is we're going to add, subtract, multiply, and divide imaginary numbers. So the two things is to express in terms of I first. What I mean by that is take the negative out of the radical and put it as I out in front, and then perform your operations just like you do on radicals. So this negative is going to come out and become an I. This negative is going to come out and become an I. I times the square root of 25 is 5 times I. Square root of 81 is 9 times I. 5I plus 9I, just combine like terms, is equal to 14I. In the second example, we're going to move the negatives out in column I. So we have 5I times the square root of 2 minus I times the square root of 32. Well, 32 breaks up into 16 times 2. The square root of 16 is 4. So we have 5I square root of 2 minus the square root of 16 is 4I, and the 2 gets left underneath, square root of 2. Those are like terms, so we can subtract. 5I minus 4I is 1I, and the square root of 2 just stays the square root of 2. So adding and subtracting, just like radicals, you need equal radicands or else you can't combine them. On this one, you're going to take the I out and put it in the numerator. This is going to be 2I over 5 times the square root of 12 minus, or not minus, times, take that out and become I times the square root of 75. All right. This is a little bit tricky because of this fraction right here. 12 breaks up into 4 times 3. 75 breaks up into 25 times 3. So you're going to take the square root of 4 and it becomes a 2 and it goes in the numerator. So 2I times 2 is 4I over 5. Remember, 5 doesn't get multiplied by anything. Just that 4 goes up to the numerator, and you're left with the square root of 3. And then you're going to multiply that by the square root of 25 is 5I, and then you're left with the square root of 3. And when you multiply two radicals, you multiply outside times outside and inside times inside. This is not a FOIL because there is not a plus sign. This is not a FOIL. It's just outside times outside. 4I over 5 times 5I. Well, 4/5 times 5, if you want to take your calculator out, you can. 4/5 times 5 is just equal to 4. I times I is I squared. The square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is 3. So you're left with 4 times I squared times 3. Well, 4 times I squared is -1. Always replace an exponent on I with what it's equal to. And 4 times -1 times 3 is equal to -12. So this answer does not have an I in it. Sometimes they don't. This is not an imaginary number anymore. Sometimes that happens. On this next example, take the I out, and you've got -5I times the square root of 80 over 2I times the square root of 45. Well, because these are outside the radical, the i's can cancel out because they're outside. All right, so now what we can do is we can do this a number of ways. We can divide 80 by 45. We can make this one great big square root and call this -5 over 2 times the square root of 80 over 45. Well, let's see. 80 over 45 reduces down. 80 divided by 45. I'm going to use my math. Option 1 frac to reduce that as a fraction, and it reduces down to 16 over 9. So this is equal to -5 over 2 times the square root of 16 over 9. Well, this is nice because 16 is a perfect square. 9 is a perfect square. And the square root of 16 is 4. It'll come out here and multiply by 5. The square root of 9 is 3. It'll come out and multiply by 2. So this is -5 times 4 all over 2 times 3, which is equal to, I think I'm going to reduce this down. 4 over 2 is 2 over 1. So -5 times 2 is -10 over 3. So this again is not imaginary, even though we started out with imaginary. All right? So those are the 4 operations: multiplying, dividing, adding, and subtracting. The last thing we're going to do, and this is pretty easy, this is a complex number. A complex number is just any number that's got a real part. This A part is the real part, and the BI is the imaginary part. So if you look through all of these numbers, you can see that they have a real part here on the left and an imaginary part here on the right. They're just like, these eyes are almost like variables. You can consider them. So what we're going to do is graph these. These are like graphing just a point on the XY axis. This is like graphing the point -8, +4. And if you wanted to graph -8, +4, you go back to -8, and you go up to 1, 2, 3, 4, and it's just a point on this XY axis. So I'm just going to put a 1 here because it refers to number 1 over here. This one is just like graphing the point +7, +9, 7, 9, because this is the real axis, and this is, you see this is the imaginary, so the Y value is like the imaginary part of this. So you're going to go over to 7, up to 9, and graph that, and that's item number 2. This one is like graphing the point 6, -5. 6 on the real axis, -5 on the imaginary, so go over to 6, down to -5, and this is number 3. Number 4, it's like graphing -9, -7. -9, -7 is down in the 3rd quadrant, right down here. This is number 4. This one is like graphing the point 0, 2. 0, 2 is on the y-axis, so 0, 2 right here. This is item number 5. This one is like graphing 5, 0, which is on the x-axis. So you're going to go over to 5, 0, and this is item number 6. And then the last one is 0, -6, which is down on the y-axis. This one is item number 7. Sometimes you'll see arrows being drawn. You don't have to put the arrows. I'm just going to take a pencil and show you, just in case you ever see this. You might see like an arrows are always drawn from the origin. So if you wanted to draw that arrow, you can point to all of these. These arrows aren't really necessary, but I'm just showing you that sometimes you see them like this. But they always come from the origin, and they end at that point. They're like little vectors, or little arrows here, going up here, and then this one comes straight across. I think I've covered them all. All right, so like I said, sometimes you'll see an arrow coming out of the origin and just going up to those, but you don't have to put them if you don't want to. And that's it for today.